So as we talk about quadratic functions and graphing quadratic functions, if you can think of when we looked at a quadratic equation, okay, and we think of what form? Y'all tell me, like, what way would we express a quadratic equation?
fx equals something, something, something.
Okay, so that's a function. So whenever you see f of x, this, that means we're talking about a function of something, and that means we're probably going to end up using a graph. In some form or fashion, we're going to have to graph or relate this to a graph, because the best way to understand functions is how they move along in a series with given certain information, okay? Now with a quadratic equation, do y'all remember what the definitions are behind it, the requirements behind a quadratic equation? First of all, what does it have to equal?
0.
0, okay. What is the highest degree term that must be present?
Squared.
Squared, x squared. So we're going to have x squared, it's going to equal 0. All right? So the simplest form would be, you know, ax squared equals 0, or maybe ax squared plus b equals 0. But what we're typically looking at is ax squared plus bx plus c equals 0. So whenever we think of the quadratic equation, okay, not the quadratic formula. The quadratic formula is whenever we plug in a, b, and c into, it had the big long square root sign. Okay, this is a quadratic equation. This is just simply a way of looking at information and how we can use it. All right. Now, whenever we get into quadratic functions, we are going to change this up a bit. But I want to touch base on this a little bit more. Simply because we are given ax, let's do this, x squared plus 4x equals 56, let's say. Okay, just because it's in this form does not mean it's not a quadratic equation. We can rename this to be in this form simply by moving the 56 over to this side. Okay, where we subtract 56 from both sides, we end up with x squared plus 4x minus 56 equals 0. Well, now we've taken this information and we've translated it or renamed it into this form that we are familiar with. Okay? And from here we can factor it out. Another way that we might have seen this is if it were x cubed plus x, let's say 4x squared minus 56x equals 0. Okay, and this was kind of a, we saw this on our last test, and it brought up some good discussion on the test. Well, this can't be a quadratic equation because the highest degree term is 3, and the definition says it must be 2. Well, just like we renamed that mathematical statement to put it into this standard form, we can do the same thing here. We just have to think about how can we? Well, if we notice, there is an x in all three of these terms. And if there is something common in all three of those terms, we can factor that out. So technically, we can rename this to where we multiply x times x squared plus 4x minus 56 equals 0. Well, now our highest degree term is x squared. We have a quadratic equation by definition. Okay, does that make sense? Isn't it amazing how we can take something like, well, there's no way this can work, and we can actually make it work? So, given that, now whenever we start talking about quadratic functions, we're going to be doing the same thing. We're going to take our quadratic equation and we're going to turn it into a different form that's going to help us with our graphing. Okay, and we're familiar with that form. Do y'all remember what it is? Can somebody tell me? Y equals what?
Oh.
There's a
Negative.
K and an H.
Oh.
And a, what is it?
No.
Doesn't have to be negative, but just the standard form is going to be what? What's the first letter?
There's an H.
There is an H involved.
There's an H and a K, but I can't remember anything else.
Okay. Can somebody look it up for me? Let's see what we have.
Is it going to be in chapter 5?
Chapter 5 is where we will see it. I'll give you a hint.
Oh, and then it's x minus h.
Okay, x minus h,
And then plus K.
Close parentheses. squared.
close parentheses squared
Oh,
plus k. Very good, I got that.
Oh.
Okay? So what's interesting and what we're going to work on from here, we've talked about being, if we look at this, how can we take information from this form and be able to get an idea of what this graph is going to look like. All right, that's what we did during the last session. Yes.
I remember if it's a negative or positive, right?
If it's a negative or positive up front,
But
what does that tell us?
if it's a negative, it goes up, but if it's a positive, it goes down.
And luckily today is opposite day, so you're correct. So yes, if it's negative, then it opens down. If it's positive, then it opens up. Okay? Makes sense? So that's one way that we're going to be able to determine kind of what this is going to look like. And again, we referred to the book cover. You can kind of read the title, you can look at the picture and figure out a little bit about what this book is going to be about. And that's what we're doing here. Now, what is it about the K? What is it? What does the K tell us?
It's not quite there.
I know. It's all right. So, and you will hear the term it is translated, which means for what it looks like on the graph, it's moved. Okay, but they use the term translated.
That would be up or down on the y.
Yeah.
Very good. It's translated or moved up or down on the y-axis. In this instance, whenever we have a positive number, then it's moved up along the y-axis in the positive direction. If it's a negative number, then it's moved down on the y-axis, okay, in the negative direction. Now, we have our y and our x, which are our unknowns, typically, okay? Now, the h, what does it tell us?
It'd be left or right on the
Exactly. It's going to be translated either in the positive or negative direction along the x-axis. This one is the tricky one, though, because this formula requires this negative to be here. So we have to take that negative into consideration. So whenever this negative exists, as we plug in numbers, if that negative stays the same, then it's moving in the positive direction. Okay, so think about it. We have the perfect formula, and H is the perfect person. And we didn't have to change that perfect person, so we're going in a positive direction. Now, if we had to change the H, that's a negative thing. They're no longer the perfect person. It's a negative effect, so it's moving along the x-axis in the negative direction. So another way to think about this would be, whenever we write this out, if this ends up being x plus some number, then you're going to go in the negative direction because we had to change this. Bless you. If this stays the same, x minus a number, then it's going to go in the positive direction along the x-axis. Okay? We will get to practice this. Okay? So just keep in the back of your mind that if we have to change anything, because think about this, if this positive here changed, well, that means we're moving it along or down in the negative direction on the y-axis. We had to change it. Well, this negative has to stay here. If it changes, then we're going in the negative direction. Okay? So a couple different ways to think about this. Now, what we're going to do is we're going to skip to section okay, we're going to go to 5.4. Okay, 5.4 is where we are. We're going to talk about how we're taking the quadratic equation and essentially turning it into this. Okay, we're still using this information. We're just going to rename this so that it'll help us with our graphing. This helped us in finding out two possible solutions that would make this statement true. That helps us as far as solving a problem, but how can we take information and end up projecting things, okay? And that's the beauty behind graphing, is we can plug in possibilities and see if it falls within our parameters. A lot of times businesses like to do this. What if we were selling DVDs and cassette tapes, okay? And this has been the way our business has been going. Well, what if we see that CDs are much more common. So what if we produced less CDs, sold less CDs, how would that affect our sales? Well, you can make subtractions and additions and see how it falls along your possible projected income for your business and your projected sales. It may also help you make adjustments within a business, make adjustments on how you're going to build a roller coaster, okay, or how you're going to design a highway. You can plug in the same information and see what it looks like and how it can be laid out through engineering, business, physics, even graphic design, interior design. If you're going to make furniture, I mean, you can use this in so many different ways, but it helps you get that visual behind what's going on. Okay, so let's look at example 1 together. Okay, we are changing the quadratic equation from its standard form here into this form here by completing the square. Looking around to see what kind of facial expressions I get whenever I use that term, completing the square. Can anybody tell me what you do if we're going to complete the square? What do we do first with the b in this form? What is the first step we do with that in order to complete the square? Remember? First of all, what you typically see is we're going to move this around. Let's take the A, B, and the C, and I'm going to put them up top. We're going to have the A. Oh, don't do that. The A, the B, and the C. So if we have just 1x squared and we have 4x and we have positive 4 will be fine, and then minus 12. Okay? Now, we can look at this, and this would, if we were to factor this, we could factor this into x plus 6 and x minus 2 equals 0. Okay, this is one of the simpler ones where we can actually figure out our factors. What are the factors of negative 12 that when added together we end up with a positive 4? Okay, and so our two possible answers here would be negative 6 and positive 2 that would make this statement true. Great, we've done that, but now what can we do with that? I got a 6 and a 2, what? Or a negative 2 actually, or a negative 6 and a positive 2. All right. Well, let's say, what's that?
I know it.
You know what?
I know how to finish it.
Okay, so what we will first do to kind of get things going, let's move this 12 over here whenever we complete the square. All right, so we're going to have x squared plus 4x equals 12. We're using completing the square method. Okay, so maybe this will help make things a little bit more familiar. So, to complete the square, what do we do with this 4 that's in the b place? What do we do? First step that we do with it, if we're going to complete the square.
Oh, we minus it. No, we divide.
Very good. Divided by what?
2.
2. Yes, we take half of this number. So let's move over here. We're going to take 4 and we're going to divide it by 2. 4 divided by 2. Okay, that equals 2. Now we're going to take that 2, half of this, and we're going to do what with it?
Square it.
Square it. Very good. Which equals 4. So we take half of this number and then we square it. And now, since we have to keep this statement true, whatever you do to one side, you have to do to the other. So we're going to add it to both sides. 4x squared plus 4 equals 12 plus 4. Right? Okay. Now we can, when we factor this, we know that we're going to end up with x plus 2 times x plus 2. That's the cool thing about completing the square, is once we've gone from here to here, we can make 2 sets of parentheses, put an x and an x, our plus and plus, and this number here is going to be half of this middle number. Every single time it's going to be there. Okay? So since half of that number was 2, it's going to be x plus 2 times x plus 2. And that will equal 16. What is another way to say x plus 2 times x plus 2?
X plus 2 squared.
Very good, which is the whole reason why we're doing this. To get to x plus 2 squared equals 16. Now, this is where completing the square, the term completing the square fits in. Now we can take the square root of both sides, the square root of both sides. So we'll move over here. X plus 2 squared equals 16. Okay, all I did was move this to here. Now we can take the square roots of both sides. The square root negates the exponent of 2, to where we have just x plus 2 equals plus or minus the square root of 16. What's the square root of 16?
4.
4. So x plus 2 equals plus or minus the square root of 4. I'm sorry, plus or minus 4. Because a positive 4 times a positive 4 equals 16, and negative 4 times a negative 4 equals a positive 16. So now, what is interesting is we can finish out this equation 2 different ways. So we can subtract 2 when this is positive 4 and subtract 2 when it's negative 4. And we're still going to end up with our negative 6 and positive 2. Okay, so we just ended up doing 2 different methods to end up with the same solution. All right? So that's to remind everybody how we are completing the square. So we are going to use this method to get from essentially from this form to this form up here. So let's look at example number 1 together. Okay? So if we were originally given x squared plus 4x plus 1 equals 0. Again, we're going to complete the square. So in order to do that, we ended up where we had We'll just follow along through here. We can section off this part here. No, I don't like the way they do that. We'll go back to the way the book is doing this in just a second. We're going to do this the way we just went through it together. And then we'll see what the book's example did. They did it slightly differently, and I think you'll understand why here in just a second. So let's move the 1 over. Okay? So we're going where we had plus 1, we're subtracting 1, we're going to end up renaming our statement like this in our example, okay? Now again, we're going to complete the square, and this example is exactly like what we were just doing. We take half of 4, which is 2. We square it, which is 4, so now we're going to add 4 to both sides. X squared plus 4x plus 4 equals minus 1 plus 4. Okay? And then we end up getting back down to, we have x plus 2 squared equals 3. Okay, we skipped a step here where we had x plus 2 times x plus 2 because we know we can rename those and combine them to where it's x plus 2 squared. Alright, well now what we can do is we can actually move this 3 over here, and we are given x plus 2 squared minus 3 equals 0. Okay? So, does this look very familiar at all, or very similar to this form right here? Notice we have a 1, that would be where A is. Just so happens there's a 1 here. Then we have our x, and here it's plus 2. All those are in parentheses, squared, plus k. So what this means is, let's identify with this right here what our values for each of these are. Y is going to be our function. Remember, whenever we have a function of something, we can take that out and put y in its place, and we're solving for y. Okay? So, since we're talking about functions, this is why we're doing this. So y equals, now a in this situation is going to be 1, because there's an understood 1 out in front of this. Okay? What is our h, the value of h going to be?
Is it going to be negative?
Negative what?
Negative 2?
Yes, a negative 2, because remember your standard form is negative h. Here we have a positive h. It got changed, so this number is going to be negative. It's actually a negative 2 is the value of h. Okay? And then our k is going to be what?
No. Yeah, negative 3.
Negative 3, yes. Because it changed this positive to a negative. It changed it so it's a negative number. It changed our standard form to something different, a different sign, so it's negative. Okay? So, we can take our quadratic equation and change it to a different standard form that helps us with our graphing. And that's what we are doing with this. Okay, does that make sense? If you look in the book, the example that they gave for this, instead of making it equal to 0, what they did is added a 4 and then subtracted a 4 at the same time to keep the statement true. That can be a little bit confusing. Why would you add something only to take it away? Well, they're adding it so that they can complete the square and make it look different. They're using it to rename it. So, if that confuses you, take this first example, let it shoot straight out your ear in the back of your brain, and don't worry about it. Worry about making it equal to 0 and using it this way, Okay, like we talked about, it'll be easier to understand. A few more steps than what this example 1 is doing. And it's really what they're doing is it's a shortcut to get there. But you can follow this. So, this is how we are starting from here and getting to here by completing the square. All right? Is this making sense a little bit more?
Yes.
I was really happy to see that some of y'all were taking a few minutes. It's like you wanted to say 2, but you're like, wait, there's some change involved. Something happened. So just remember, if it changes something from the standard form, if it changes the sign, that means it's going to be a negative value for either h or k, depending on which one you're talking about. Okay? So let's do example 2 together on 3.4. Let's do example 2. So we have function of x equals 3x squared minus 6x plus 7. Okay? Now as we do this, think of where it equals 0. We're going to kind of switch the side, everything on the other side of the equal sign and work down with this, okay? So your function of x is normally where your 0 is, but what we're doing is we're finding a value for y there. So let's work from here all the way down. So, what makes our life a little bit easier, if we can avoid having a constant attached to this x squared, then whenever it comes time to factor, it makes things simpler for us, okay, as opposed to having to include that. And we notice here that if we do this, 3x squared minus 6x equals minus 7, well then we can factor out a 3 out of this part right here. So we can have 3 times x squared minus 2x equals a minus 7. Alright, now we can go through and complete our square from here. What is half of 2? 1. And what's 1 squared? 1. Very good. 17 and a half. Can't trick me with that one, teach. Yes. So we'll keep the 3. We'll have x squared minus 2x plus 1 equals minus 7 plus 1. And so we'll have 3, and it's going to be x minus 1 squared. Because again, we have to take into consideration what is a factor of 1 that gives you a positive 1 but ends up with a negative 2 when you add them together. So a negative 1 times a negative 1 gives you a positive 1. But when we add negative 1 plus negative 1, we get negative 2. So here, 3 times x minus 1 times x minus 1 equals a minus 6. Or we can rewrite that as 3x minus 1 squared. Now we're going to go ahead and move this 6 back over, plus 6, okay, equals 0. Or what we're doing here is, since we're talking about functions, we bring this down. So the function of x equals 3 times x minus 1 squared plus 6. Does this make sense?
Not the last 2 steps.
The last 2 steps. So, what we did, like from here and here?
Yeah, because
Okay, do you know how we got here?
no.
Okay, what factors of 1, what are factors of positive 1? So we have 1 times 1. What else will give you a positive 1?
Negative 1.
Negative 1 and a negative 1. Negative 1 times a negative 1. Now, which one of these, when you add them together, gives you a negative 2? Got it? And then all we did is from here we renamed it because an x minus 1 times x minus 1 is the same thing as x minus 1 squared. Now, this looks way, way, way too familiar to this form right here, right? We have, so let's figure out our values. We've renamed this statement into this form so that it makes our life easier to graph. So what is the value of A over here?
3.
Does everybody see that? The value for A over here is 3. Positive 3. What is the value for H?
-1.
1.
Positive.
Why is it a positive 1? Why is it a positive 1?
Because it's squared.
Because it didn't
Because
change.
it didn't change.
It didn't change.
Right, it did not change the original form, okay? The original form, it didn't change that sign. It is still negative right here. So this value here is going to be positive. Now what about K? What's the value for K? Positive or negative? Why?
Because it also didn't
Correct. It did not change the original form or the original value or the original sign. Okay? So now we have our values. So we can look at this. Does this open up or down?
Up.
Up. In the positive direction because it's positive. All right? So along the y-axis, how is it translated? What's that?
Negative.
Up
Are you
1
talking
second,
about
negative
up
6.
6? Over 1, up 6?
Okay?
Is that?
So it is going up 6 in the positive direction because K determines our y.
What's in the y is that?
What's
in
in-
the y is that?
Why?
Y. Okay, up and down is y, right and left is x. So the K tells us how it's translated along the y-axis. Okay? And so it's going up 6 in the positive direction. Then the H tells us how it's translated along the x-axis. So it will go in the positive direction along the x-axis 1. This is where identifying your values will help you when it comes time to create begin building your graph. Okay, and whenever it's asking you how this is translated. If you take this, go ahead and list your A, H, and K, then you know I've got a positive number here, it's opening up. There was no change for the sign in front of the H, so my H is a positive 1. There is no change for the sign in front of the K, so my value for K is going to be positive and it's going to be 6. All right? Now, this information, which is extremely important, is we can determine our vertex. So we have 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. We know this opens up. We know that for the K, it goes up. It's translated to 6. 1, 2, 3, 4, 5, 6 right there. But it's also translated in the positive direction 1 unit along the x-axis. So over here. So this is our starting point. This is our vertex. Our vertex is going to be 1 and 6. We found the first of at least 3 values that we need for our parabola. Really, for a parabola, I always suggest trying to find 5 values. Find 5 points to help confirm that you are doing this correctly and it's going in the direction and shape that you anticipate it to. Okay? So this is, we already know without doing any plugging in any values, we already know one of our coordinates. It's going to be 1 and 6. And we know it's going to open up some direction. Now from here, since we know our values, we can plug in, we can do this, x and y, and then we can plug in values for x and solve for y.
I have a question.
Yes.
With the 3 on the beginning,
Mhm.
doesn't that help you graph part of the problem too, or like
Not-
over 1 up 3?
No.
No.
No, it's just, no, because the only way that it's moving up and over are your H and K. The significance as far as the initial visual of how this is going to be is if it's going to be a positive or negative at this
Okay.
point, okay?
Now, does it work the same way in 5.3?
What do you mean?
Because in 5.3, I used the number on the beginning to help graph.
Now, it will help you graph. What's going to happen is whenever you plug in your value for x, you have to use that 3 to help solve for y.
Okay.
Does that make sense?
Mhm.
So here, let's use positive 1. Well, no, let's use 0. We'll use 0 for right now. So if we have 0 for x, let's see. Does everybody have all of this top part?
Mhm.
Okay, I'm going to erase this so we can work. So I'm going to rewrite it. Fx equals 3x minus 1 squared plus 6. All right, so now we have y, because we're solving for y, 3 times 0 minus 1 squared plus 6. So 0 minus 1 is still minus 1. Minus 1 squared is 1. So we have 3 times 1 is 3 plus 6, which equals 9. So when x is 0, y is 9. We had to use that 3 to help us in our calculation for finding our additional points, but our initial translation or getting our visual of what this is going to look like, we only need to worry about the whether it's a positive or negative right now, okay? Keep your mind open for some more use of this formula, but at the beginning stages, this is all we need to focus on. So here, when x equals 0, y equals 9. 6, 7, 8, 9. Okay, so we have 0 and 9. Well, what if x equals... Yes, go ahead.
See, if you had gone over 1 and up 3, you'd have gotten the same answer, right? Because that's what I did. So I'm just confused because I used the 3 over 1 at the beginning of the problem, and I kept getting them right when I used it. And see, if you took the 3 over the 1 in front of the problem and moved over 1 and up 3, you would get the same as 0, 9.
Over 1 and up.
Starting from the point
Oh,
up
from
there.
here?
Yeah, that's how I did it in 5.3.
Okay, yes.
But I'm
And
not
that's why I'm saying, but here, what we're talking about is where is your vertex going to be? Okay, we're looking at our starting point. This is used, that 3 is used, and it has a very significant play in where basically a pattern from the starting point, and as you move along, you can see a sequence taking place. So you're right with that. But what we're looking at here from the very beginning is basically we're finding our vertex and just getting an idea of about what it's going to look like roughly. Does that make sense? So, yes, you're right, but to start off with the vertex, we don't need that 3 yet, okay?
Okay.
Notice here, our vertex is 1 and 6.
Mm-hmm.
Okay, or negative 1 and 6, and so we're able just to look at what our value is for h and k to start off our parabola and find our vertex. From there on out, yes, you will start noticing patterns based on, say, this 3 up front,
Okay.
and then you're going to notice a consistent sequence taking place.
Okay. So it wouldn't be wrong to do it that way?
Oh no, absolutely
Okay.
not. No. What you're doing is good. Okay, because you're able to read it more.
I have done all that homework wrong.
No, you didn't do it wrong. Now, if you're able to recognize that, that is great. That's one way of viewing it. If that throws you off, then do it the long way and find your values, and we're going to see how this transpires, okay? So let's do, let's use, we'll use 4. Where, let's see, where the value for x is 4. So we have 3, 4 minus 1 squared plus 6, which equals 3 times 9. Is 4 minus 1 is 3, squared is 9, plus 6, which equals 27 plus 6, which equals 33. So whenever we move over 4, 1, 2, 3, 4, then we will go up to 33. So 9 goes all the way up to here. Okay, and then as we put more dots up here, we will see it end up taking shape, and you can actually use, 1, 1.5, you can use 2, 2.5 if you want to. What I suggest is look at your initial problem here and identify numbers that will be easier for you to calculate, okay, whenever we do calculations like this. Okay? And then what you can do is any point, if it happens to fall on 5 and 109, you can plug those values in and this statement will still end up being true. Okay? So basically 109 equals 3 times 5 minus 1 squared plus 6 and whatever. Make sense? Okay, good. Because I want to stick with these basics right now, being able to calculate this out, and then we're going to see how this keeps transpiring. You can keep sticking with that, especially if you find that what you're doing is correct.
Okay, I'm not sure how to get more than 1 point out of it. But
Well, and the difficulty with that is because it doesn't always end up with, you're not always going to end up on a whole integer necessarily. And so that's where graphing can be difficult. It's better to deal with whole integers with your values so that you end up with that. So does that make sense?
Yeah, it does.
But you will start noticing patterns as you start doing this. But anyway, so does everybody understand, one, how we moved from our quadratic equation over to this standard form, our quadratic function form? Okay? How to read this and be able to translate it so that you can identify what your vertex is. Okay? And then you have your line of symmetry, which is going to go through that vertex and will basically turn this parabola, or cut the parabola, into 2 equal parts. Okay, so you will have a line that goes straight down this vertex that will turn that parabola into 2 equal halves. Make sense? Because remember we were talking about that, how you can take a box and you have several lines of symmetry that would cut that box equally in half. It's the same thing, and they will ask you to identify that. Awesome. Does everybody feel a little bit more comfortable with completing the square now too? Mm-hmm. Okay, good. All right, let's turn to 5.5. Can somebody read out the title to 5.5?
Problem solving using quadratic functions.
Awesome. Which means what? Somebody restate this title into, say, 2 words. What is everybody's
Word
type
problem.
of? Yes, word problems. Oh, and I love everybody's smile on their faces. This is great. So what's interesting is y'all gripe and moan, but let me ask you this: whenever somebody presents you with a problem, pay attention and look at their face whenever you say, "Can you please present that problem to me in a form with letters, numbers, and evaluative symbols?" they'll be like, what? Yeah. So it's easy for us whenever we have it all laid out here. It tells us what the problem is in a mathematical sentence, but that's not typically how we have to come across problems, how we're presented problems. We're presented problems with somebody walks up to you, hey man, I have this and this and this and this and this is what I've got to do. Or Billy Bob Joe and home dude with the shoes are trying to get someplace and this is what happened. So then you've got to collect all that word information, put it in symbols, and then be able to work that mathematical statement. Okay? So the ability to do that is very necessary. If you take a second language, it's very much the same thing. Okay? If you take Spanish or German or French or Italian, you're learning that language, but what you're also doing is translating English into that. What you know about English, and you're trying to figure out what the final result is going to be so that you can be effective with it. So don't let it beat you down. Don't immediately cringe and stick your head in a hole in the sand or something and have your feet kicking, because that's just kind of weird looking. But think about it as, you know what, I can do this because this is easy. Because I know how to read properly. I know how to plan properly. I know how to solve, and I know how to check my work. The 4 essential rules with word problems. And so we're going to work through a couple of these together. What's that? Yeah. Okay. So we learned in the previous section how describing a graph and how it is in the form of a function, a quadratic function. So the function of x equals, and then we see our standard form up here. Okay, looking at the graph that accompanies this particular function on the top of page 187, we have the function of x equals minus 2 times x minus 3 squared plus 1, and this is what's shown. Okay, we see that it's a negative 2, so it opens down. The k is a positive 1, so it's translated up 1 unit on the y-axis. And then we have a negative 3. Okay, it did not change its original form, which means that the value of it is a positive 3. So it's translated to the right or in the positive direction on the x-axis. This function has a maximum point of 3.1. So the vertex in this situation is the very tip, the maximum, the most that will make this statement true. Just like earlier over here, 1 and 6 was the minimum, the very minimum it had to be in order to make it a true statement. Down there is, whenever it goes down, there is a maximum it can be. Everything below it is infinity, as long as it falls within those parameters. All right. What's interesting is if you look at this from a perspective of a projectile, if you're standing on the ground and I take this marker and I chunk it up in the air, there is going to be a maximum point that it reaches where it's going to stop, peak, and then make its way back down.
Can we try that?
Here, I'll borrow your phone, and we'll go with that. Yeah. So think of that as a projectile. Okay, it's a good way of thinking about it. So if we look at example 1, it says a projectile is shot vertically from the ground level at a rate of 992 feet per second. Disregarding wind resistance, the motion of the projectile is described by the equation h of t equals minus 16t squared plus 992t, where the h function of t represents the height above the ground in t seconds. Okay? What is interesting about this particular setup, what it's talking about here is gravity. Okay, I'm sorry, I just lost the word for a moment. This particular formula comes from physics for projectile motion. The negative 16, if you'll look at it in the formula, 16 is the value for gravity, and the negative sign indicates the direction of the motion. Okay? Now, I know a lot of you are like, well, that's all good and fine. I took Algebra 2, not physics. So can we skip this or what? Well, unfortunately, you're going to have to understand this. It's bleeding in some physics, but we don't have to understand necessarily the physics behind it, but what we do understand is the equation that it gave us. That we can work, okay? We'll work it and we can graph it. All right, so if you look further down, where it begins simplifying or renaming it, we're looking for the maximum height it will reach. What is that called?
Vertex.
The vertex, okay? Which is great. Does that mean you're really going to have to do a whole lot of math? Yes, you will. So just
Everything's fine.
get over it, yeah. So we have this equals minus 16t squared plus 992t. All right? We can actually factor out minus 16 out of both of these to where we're left with t squared minus 62t. Okay? Now, from this point, you're like, okay, I get that, I did the factoring, but I'm stuck. I don't have a 0, I see the y, but I know I'm supposed to have a k somewhere. I forgot what I'm supposed to do with this. What is the step to continue from here? What is it called? COS or CTS. Completing
The square.
Square area. Yes, completing the square. Very good. Hooked on Pohenix, worked for me. So we're going to complete the square, okay? We need to be able to get it in this form, so let's complete the square. We know how to do that. You take half of 62, and then you square that, which ends up being 961. But you do that to both sides, and then we'll skip down. We end up with minus 16 t minus 31 squared. What's cool is we can go ahead and write this statement out here without doing any mathematics other than taking half of this. Okay, the negative sign still stays the same, but we take half of that. Half of 62 is 31, so this part we're already done. The only math we really have to do is 31 squared. Okay? So then we have 31 squared. So we have 961, 31 squared equals 961. But remember, whenever we add this, whatever you do to one side, you have to do to the other. The shortcut is that we'll end up doubling this ultimately. But we're, one second, 15, 376. This is where we're going to end up. Okay, so remember, we take half of this, square it, okay?
So you took
make
half
sure it
of
applies
62?
half of 62,
Okay.
yes. And then you end up squaring that, which ends up being 961.
So how do you end up with 15,276?
Very good. How do you think we end up with this? Because we skipped a step, actually we skipped 2 steps to get there. So let's think back. Whenever we had, let's see, we'll go, I want to go far away. We'll go over here. Minus 16t whoops, minus 16, t squared minus 62t. What do we normally see after here for a quadratic equation? Equals what?
Zero?
Equals 0, yes. Okay? So, now we completed the square here. Half of 31, or I'm sorry, half of 62 is 31. Squared is 961. So what we're doing is minus 16 t squared minus 62t plus 961. Okay, equals 0. Now, whatever you do to one side, you have to do to the other. So, if we add 900, equal, let me rewrite this, minus 16 t squared minus 62t plus 961. If we say equals 961, we added it into these parentheses, and we're adding it to the other side of the equal sign.
Is it 16 times 961? Is that what it is?
Why would it be that way? Without looking at your book, why would it be that way?
Wait, because don't you have to add the 961 onto the other side too?
We did. We added it inside the parentheses, and we added it on this side. But why is it simply adding 961 to this side, not changing the statement? It no longer made this the same statement.
Well, because what we have to add to one side, we have to add to the other.
Yes. We added 961 inside of these parentheses. What is outside of these parentheses that's affecting every single one of these terms?
Oh, we would
Negative 16.
We would have to times the equals 96 one times.
Yeah.
Yes.
But why? Because the problem gave us that. It's not like we added the 16 on ourselves.
No, they skipped 2 steps. Assuming you understood why, they skipped 2 steps to just get to that amount. But what you have to understand is, this statement is saying we're going to take negative 16 times, and we're going to multiply it times t squared. We're also going to multiply it times negative 62t, and we're also going to multiply it times 961. You can't just throw in 961 by itself, even though it's really being affected by this negative 16. And then simply add it to this other side. You have to multiply this times anything on the outside, then add that amount to over here. Does that make sense?
Yeah, it does. Because
So-
it's not going to be just 961 by the time you finish.
Right.
So you have to, yeah, that makes sense.
Does that make sense, or who's confused? Because this is very important.
Back row back here.
So just realize, whenever you get to this point here, okay, instead of just adding it, check on the outside of the parentheses. If there's something there, you have to multiply this number times that number. Because if you think about it, if you plug this back in, you use the distributive property, and you plug this back into each of these, you're going to end up with, I don't know what number, but it's negative 16 times 961. Well, that's what you're really adding to this side. Because you factored out the negative 16 from both of these, well, you're also factoring it out of the 961. So what you're really adding to both sides is 961 times negative 16, so you have to add that amount to both sides.
Wait, over there you have plus 1500.
Because we ended up moving things back over here. Negative 16 times a positive 961 gives you a negative number. Whenever we move it back, it will be positive because it's that. Negative 16 times 961 gives you a very large negative number. You bring it back over, it turns positive, and you will add that number to 961, which results into this magnificent 15,376. Does that make sense? Yeah? Okay.
It'll click, Claire dividers, let's hope Claire carries over to the helper. Yeah, let's hope we remember it.
So, just remember, pay attention and work this step by step and make sure you include whatever is outside these parentheses. Okay? All right, let's move on. So, from here, now that we've found this, we know what our vertex is. We know that this is going to be our y value, and we know that since this didn't change from its original form, the positive 31 is going to be our x value. So our vertex is 31, in the x, and then 15,376 in the y. Okay, so from a projectile standpoint, 31 for the x and 15,376 for the y, that coordinate point is the peak that projectile is going to reach before it starts falling back down. That is its maximum. Make sense? So we had to do a whole lot of stuff to make it simple so that we don't have to do any math. We did a lot of math so we didn't have to do any math. Make sense? Makes perfect sense.
When you don't think about it.
Yes, when you don't think about it. When I'm not paying attention, it's great. Okay, real quickly, let's go over, I'm going to go over example 2 as well, okay, so that we can work through a word problem. Let's read this together and then we'll work through it together. Does everybody have this, and can I erase it? I am very, very glad you asked that question. I was going to bring it up later, but I'm glad you asked it because it means that you're looking for something that doesn't seem to be right. It's not making sense, and wanting to know how to understand it makes a world of difference. So good job. Okay, so example 2, page 188. 188. An airline flies between two major cities daily. It normally transports 81 people a day, okay? It normally transports 81 people a day at a cost of $210 per person. The airline estimates that it will lose 2 passengers for every $6 that it increases the fare. What should the airline charge to gain the maximum income? Okay, what should they charge to gain the maximum income? They know that for every $6, they're going to lose 2 of their passengers. That every $6 that they increase the rates, they're going to lose 2 passengers. So for every $6 that they charge everyone else, they're going to lose $420 because they lost 2 passengers. So it's asking us, what is the maximum rate that they should charge so that they can capitalize? They understand they're going to lose a percentage of people, but they can make a little bit more money if they increase their rate. Okay? So what we're going to start off with, it says, what should the airline charge to gain the maximum income? Okay, what should the airline charge to gain the maximum income? So, we're talking about $6 increases. So what we're going to do is we're going to say let x equal the number of $6 increases. Okay? Our unknown is how many $6 increases should we have. Alright? Now, the price per person is 210 plus 6 times x. $210 per person plus 6 times x. Let's look at this real quick. Where'd I go? Okay, so let's do this. Let's assume that there were 2 increases, okay? The price per person is 210 plus 6 times x. Okay, so let's say that there were two actual increases that took place. All right, just to throw this up there, then we can calculate the price per person would be 210 plus 6 times 2, which is 12, and that's going to equal $222. Okay, we could also calculate a new number of passengers whenever we know that we're given that passengers is 81 minus 2x. Okay, 81 minus 2x. And let's do that over here. So if we had if we increased it by 2, 81 minus 2 times 2, and that's going to give us 77. So what we're looking at is it's a 200, where we had 81 passengers originally at $210 per person. We're now charging $222 for 77 people. We know that after the increase and the possibility of losses, we can now figure that at $222, we will have 77 passengers. Well, let's figure this out. If we had $210 for 81 people, then that gives us 0, 1, 2, 0, 8, 16. 16, 1, 7, 0, 1, 0. All right, well, if we did 2 increases, and we have it at $222 per person, but now there are only 77 people flying, we have 4, 5, 15, 4, 5, 15, correct, 14, yes. And so we have 4, 9, 0, 5, 6, 7, 1. Okay, now we have found that we have increased our profits by $84. Okay, now, not significant, but over the long period of time, it can be a significant increase. That may take care of all of your toiletries for all of your flights. You know, there's no telling. Now, what we did is we threw in possibilities to see if it would work or not. Okay, we picked 2 to see if that's going to help us or hurt us. And then what we could do is pick, okay, what about 2.5? Well, what about 3? And then try to hone it in, and we keep going through this formula multiple times, and it's hit or miss. It's trial and error. And it's not a very efficient way of figuring this out. Okay? So let's try to be more efficient. Just to kind of go through quickly, if we if you increased it, say, 5 times, you may have increased the price so much that you decreased so many passengers that you're now making less than $17,010. Does that make sense? So there is a point where, if you think of it graph-wise, where now you are actually losing money, but what we're trying to find is here. We may be starting off here, that 2 gets us here, 5 gets us maybe over here, to where now we've gone past this perfect peak. What is the optimal thing that we want to, or the optimal price we want to get to? And so that's where we're going with this. So what we can do is take our information and put it in the form of a function, which is what it shows us here. We can take our information and put it in the form of a function. Now, we have a quadratic equation here that has been factored. Okay? This looks very similar to us. If we want to, you could technically rename this as minus 2x plus 81 times minus 6x plus 210, if this helps you visually. Okay? Because we're used to seeing the x's on the left side and our constants on the right side. All right? Now, what we can do is we can end up going the opposite direction of the FOIL and end up with our quadratic equation. So let's do this looking at the book instead of actually throwing up all the numbers if we follow along. But from here, from this point, you'll see the next step is at number 3 where it says solve. So we've combined it from the factored term, now they've turned it into a quadratic equation. And then from there they complete the square and they end up getting it into this form, which is where we end up at the bottom of the list where it says solve. So we have our function equals minus 12 times x minus 2.75 squared plus 17,170 cents, or 75 cents. Okay, so here we found that it is at 2.75 is our maximum times that we want to increase the rate. Okay, that puts us at our best peak. Anything higher than that, then we are going to start going back down and not getting as much money as we possibly could. Okay? So all we did is we took our information, turned it into a quadratic equation, renamed it into a quadratic function form, and then we can graph it, and we don't even have to graph it from that point. Once we changed it, we can know what our vertex is, and our vertex is our peak point. Okay? All right. Your other word problems are going to be very similar to that. Now, let's look at 5.6. We're going to only go over this very quickly because this is the exact same thing as equalities.